I see that directly tackles the problem of imbalanced classes. It assigns weights to each class, giving more importance to the minority class, the churners in this case, which helps balance the model's learning and improves prediction for the minority. Think of it like giving a louder voice to the underrepresented churners so the model hears them better. Here is key. By using only 80% of the data for each tree in the gradient boosting model, I reduce overfitting. Overfitting happens when the model learns the training data too well, including the noise, which hurts performance on new data, especially with class imbalance. Subsampling improves the model's ability to generalize to unseen data, making predictions for both classes more reliable. It's like making the model more robust and less sensitive to the quirks of the training data. A learning rate of 1.0 is too aggressive for AdaBoost. I believe a high learning rate can cause overfitting. The model might become too focused on individual data points and fail to capture the overall pattern, resulting in poorer performance. It's like trying to learn too quickly. You might miss essential concepts and get the final answer wrong. Bagging, which stands for bootstrap aggregating, creates multiple models from different subsets of the data, then combines their predictions. Just means 100 models are built. While effective for general improvements, bagging doesn't inherently address class imbalance directly. It's a robust technique but not the best solution for this specific problem. It's like having a large team, but if they all have the same bias, the final outcome won't change. This is the overall topic. We're using ensemble methods, multiple models working together, to predict customer churn, which is a situation where a customer stops using a service. It's particularly tricky because we have many more customers who don't churn than those who do asterisk, which is called class imbalance. This is the core question: which ensemble method, with proper settings, works best when one class, non-churners, has far more examples than the other, churners? We want to avoid misclassifying churners. I'll use a random forest. The class underscore weight equals balanced argument tells the model to pay more attention to the smaller class, churners, by giving its examples more weight during training. This directly tackles the imbalance problem, making it more likely to correctly predict churn. Here, I'm using gradient boosting. Subsample equals 0.8 means that for each tree in the forest, I only use 80% of the data. This helps prevent overfitting, a problem where the model learns the training data too well and doesn't generalize to new, unseen data. Overfitting is particularly bad with imbalanced data. By reducing overfitting, we improve prediction accuracy for all classes, including the minority, churners. I tried AdaBoost, but setting learning underscore rate equals 1.0 is too aggressive. It can lead to overfitting, especially in an imbalanced dataset. The model might get stuck on the majority class and ignore the churners. Bagging uses many decision trees. While increasing n underscore estimators the number of trees, can improve performance, it doesn't inherently address the class imbalance issue. The model might still be biased towards the majority class. Option A is correct because it directly addresses the class imbalance. Option B is correct because subsampling prevents overfitting, which helps with imbalanced datasets. Option C is incorrect because a high learning rate can cause overfitting, especially for imbalanced data. Option D is incorrect. While bagging is robust, it doesn't inherently solve the class imbalance problem. Great job. I see this as the main topic. We're diving into how different machine learning methods handle datasets where one category has way more examples than another, a common problem in real-world data. This is crucial because it impacts how accurately we predict the less frequent group. We'll explore techniques that help address this imbalance, allowing you to build fairer and more effective models. This is the question that sets the stage. We want to find the best group of methods that are good at making predictions when the data is imbalanced. The focus is on techniques that improve predictions for the underrepresented class. Let's break this down. Random forest classifier is a powerful method because it combines many decision trees. The class underscore weight equals balanced part directly addresses the imbalance by giving more weight to the minority class during training. This helps to make the model pay more attention to those underrepresented cases, improving their predictions. I see this as a strong option. Here, Gradient boosting classifier is another powerful method. The subsample equals 0.8 feet parameter controls how much data is used to train each individual tree within the ensemble. By using a fraction of the data, 80% in this case, we reduce overfitting, making the model more robust and better able to predict the minority class more accurately even though it doesn't explicitly target class imbalance. I like this approach too. ADA boost classifier is another ensemble technique, but setting the learning rate to 1.0 is too aggressive. This can lead to overfitting, meaning the model learns the training data too well but performs poorly on new data. This is particularly problematic with imbalanced data, worsening the predictions for the minority class. I would avoid this setting. Bagging classifier uses multiple copies of the training data to build separate models. While useful for reducing variance and improving accuracy, it doesn't inherently address class imbalance. While increasing n_estimators, number of models, may help a bit, it won't fix the class imbalance problem by itself. This refers to the improved model performance specifically on those rare events. We are looking for methods that help correctly identify the minority group, improving recall, precision, and F1 score for the minority class. This is an important goal of the problem. This highlights the risk of choosing unsuitable methods or hyperparameters. It indicates that some choices might harm the model's ability to predict the minority class. We need to be cautious and understand the potential pitfalls of each approach. This instruction means there could be multiple correct answers. I need to carefully consider each option to find all that best handle imbalanced data and improve minority class performance. This section introduces the core topic, using ensemble methods to handle datasets where one class, like churners, in customer churn prediction, has far fewer examples than another, like non-churners. I'll explore how different ensemble methods can be more effective at this than simpler models. This question directly asks us to pick the best ensemble learning method from several options. I'm focusing on how each option's parameter settings specifically help with the problem of having too few examples of the churners class. Gradient boosting is a powerful technique. The subsample parameter controls what fraction of the training data is used to build each tree in the ensemble. Setting subsample to 0.8 means 80% of the data will be used for each tree. This helps prevent overfitting, a common issue when dealing with imbalanced datasets, which will, in turn, improve minority class prediction. Overfitting means the model learns the training data too well and does poorly with new data. It's like memorizing the answers to a test instead of truly understanding the material. A random forest is another powerful ensemble method. The class_weight equals balanced parameter tells the model to assign more importance to the minority class, the churners. This helps balance out the model's focus and prevents it from ignoring the minority class because it has fewer examples. It's like giving more weight to the harder problems in a test. AdaBoost is an ensemble method that focuses on difficult to classify instances. However, a learning_rate of 1.0 is quite high and can lead to overfitting. In the presence of class imbalance, this high rate can worsen the model's already inherent bias against the minority class. I don't advise using this parameter setting. Bagging is a good method to reduce variance, which helps the model generalize better. The number of estimators, 100 in this case, affects performance. However, bagging itself doesn't directly address class imbalance. It's more of a general-purpose method to improve model robustness. For an imbalanced dataset, there are more effective strategies. Based on my analysis, options A and B are the most effective for handling the class imbalance problem in this particular scenario. Option A, random forest classifier with balanced class weights, directly addresses the imbalance, while option B, gradient boosting classifier with subsampling, indirectly helps by reducing overfitting, which often worsens the problem. This section introduces the core problem, using ensemble methods in machine learning to predict customer churn, which is especially challenging when dealing with an imbalanced dataset, more non-churners than churners. I'm focusing on how to improve the model's accuracy for the minority class, the churners, which is often overlooked by standard models. This is like trying to find a few needles in a very large haystack. This question tests my knowledge of different scikit-learn ensemble methods, like random forests, gradient boosting, AdaBoost, and bagging. I need to select the method and its settings that best predict churn in an imbalanced dataset. The key is selecting options that either directly or indirectly handle the imbalance. I'll use a random forest classifier here. The _class_weight equals balanced parameter tells the model to pay more attention to the minority class churners by assigning weights to each class inversely proportional to their frequencies. This directly addresses the imbalance problem, making it more likely to correctly identify churners. I think this one is a winner. Next, I'm using a gradient boosting classifier. Subsample equals 0.8 means the model uses only 80% of the data for each tree it builds. This helps prevent overfitting, a common problem when dealing with imbalanced datasets that can lead to poor performance on the minority class. This is a good strategy because it focuses on generalization. A less overfit model is more likely to accurately predict the churners. It's an indirect but valuable approach. Here, I have an AdaBoost classifier. A learning rate of 1.0 is quite high. In AdaBoost, a high learning rate can cause overfitting, which is especially harmful with imbalanced data. It may make the model too sensitive to the majority class, harming the prediction of churners. I don't like this one, it's too aggressive and likely won't help. Lastly, I have a bagging classifier using decision trees. While increasing the number of estimators, n_estimators equals 100 generally improves the model. Bagging doesn't inherently address class imbalance. It's a good technique, but it doesn't directly tackle the imbalanced data issue. I don't think this will improve predictions of churners. Options A and B are correct because they address the class imbalance problem, either directly, A, or indirectly, B, by preventing overfitting. Options C and D are incorrect because they are unlikely to improve the performance of the model on the minority class. C uses an aggressive learning rate which could overfit, and D doesn't address imbalance directly. This section introduces the core topic, using ensemble methods, which combine multiple models, to handle datasets where one class has far fewer examples than another, imbalanced classification. We'll explore how different ensemble techniques and their settings can better predict the less frequent class. This sets the stage. I'm looking at several ensemble methods to find the best ones for dealing with class imbalance problems in machine learning. Gradient boosting is one approach. I'm using a parameter called subsample set to 0.8, meaning 80% of the data is used for each tree in the model. This helps prevent the model from overfitting, which is especially important when classes are imbalanced because it can make the model less sensitive to the majority class and slightly better at predictions for the minority class. It's like having a team of experts, but each only looks at a part of the data to make their own decision, so you get a more robust and diverse opinion. A random forest is another ensemble method. Setting _class_weight equals balanced tells the algorithm to give more importance to the minority class during training, which directly combats the class imbalance. It essentially increases the weight assigned to the underrepresented class, balancing its influence. Think of it as giving a louder voice to the underrepresented group during a team discussion. AdaBoost, with a learning rate of 1.0, is generally not the best choice for class imbalance. A high learning rate can make the model overly sensitive to individual data points, potentially exacerbating the problem if there are many more examples of one class. It may overfit on the majority class, neglecting the minority class, so it's not a good option. Bagging, bootstrap aggregating, even with 100 estimators, trees, doesn't directly address class imbalance. Bagging is good for variance reduction, but it doesn't focus on improving predictions for the minority class in itself. In this quiz, options A and B are the correct answers as they best address class imbalance in these scenarios. I need to pick all options that effectively deal with class imbalance. Options C and D are incorrect, meaning these would not be ideal for class imbalance problems.